this video, I'm going to talk about the concept of definite integration. We may treat the definite integration as the process of finding the area under a curve. In this simple example, we have the curve to be y equals x squared, and we want to find the area under the curve from x equals 1 to x equals 3. In this way, we can represent this area by this notation. X squared is the function of the curve, and dx means that this function is in terms of x. That means x is the variable concerned. And then 1 here is the lower limit, 3 here is the upper limit. That means the area is from 1 to 3 in terms of x. Actually, there is a very straightforward way to find the value of this area. But before that, let's take a look at a more complicated but direct method to find this area, so that we can understand the whole concept better. The complicated way to find this area is to divide the figure into rectangles. Of course, we know that now the sum of the areas of these rectangles is not exactly equal to the area that we need. But when we have more divisions of rectangles, the estimation should be better. And then we can consider the limiting case in which the number of divisions tends to infinity. Then the limit obtained should be exactly equal to the area under the curve. To do so, first of all, we should assume that there are n divisions. And the width of the ith rectangle is delta xi. Please note that the widths of all the n rectangles are not necessarily to be equal. But for simplicity, in this example, we can assume that delta xi is the same for all I. And then we can denote 1 to be x0 and 3 to be xn. Then we have x1 here, x2 here, so on and so forth. In this way, the sum of the areas of these n rectangles is equal to this. This part means the area of the ith rectangle. And this summation sign means we're going to find the sum of the areas of all the n rectangles. And then this limit sign means we're considering the limiting case in which the number of divisions tends to infinity. And this limit should be exactly equal to the area that we are interested in. xi star here means any value of x between xi minus 1 and xi. We can refer to the figure. xi star means any value of x lies in here. And then xi star square is the height of this rectangle. Because the function is x squared, so when we take square, we can obtain the height of this rectangle. In other words, the height of this rectangle can be from here to here, or from here to here, or any value in between. It is known that no matter we consider the height of this rectangle as xi minus 1 square, or xi square, or any value in between, it will not affect the final result of this limit. Because when n tends to infinity, these two values of x are very close to each other. Once we can understand this limit notation, then we can understand why this notation makes sense. Dx can be regarded as a very small delta x, and x squared dx can be treated as the area of a small rectangle. And this means that we're going to find the sum of the areas of all the small rectangles. Now we can try to evaluate this limit. If we assume that the widths of all the rectangles are equal, then delta x is equal to 3 minus 1 over n. And then we can pick xi star as xi, so that we can have this expression. Now we can take out n in the summation sign, because in the summation sign the variable is I, but not n. So n is just like a constant for the summation. And then we can simplify this as this. After further simplification, we can obtain this summation formula, and then we can evaluate this in terms of n like this. To make this video short, I'm not going to talk about the details of how we can evaluate this summation. But the key concept is to evaluate the summation I and summation I squared. And these formulas can be proven by mi. After evaluating the summation, we can now evaluate the limit in this way. And then we can see that the result is equal to 26 over 3. From this process, we can see that finding the area by limit can be very complicated. That's why I'm going to show you another method to find the area under the curve. The other method to find the area under the curve is to first of all consider indefinite integration. If we integrate x squared, we can obtain 1/3 x cubed plus c, and we can simply omit the plus c. And then we should use square brackets to enclose it, and then put down 1 and 3 here. This square bracket notation means we're going to substitute 3 into the function, and then 1 into the function, and then subtract them. As a result, it is exactly equal to 26/3. From the subtraction, we can see that y the integration constant plus c can be ignored, because the constant will be cancelled anyway, so we can simply omit it in the first place. As we can see, this method is magical. It involves a few steps, but we can obtain the value just the same as the one we obtained in the limit. To make this video short, I'm not going to explain why it works. The proof of this method will be in another video. Now let's put the concept in general terms. Suppose we want to find the area under the curve y equals fx from x equals a to x equals b. We can obtain this area by the limit formula, or by considering the indefinite integration and then subtraction like this. This capital Fx means a primitive function of this small fx, and this formula is known as the fundamental theorem of calculus. The proof of this theorem is in another video, and right now we can just accept this result. Now let's learn some terms. This notation is actually called the definite integral. And then a here means the lower limit of the integral, and b is the upper limit of the integral. The capital Fx, as I have mentioned before, it is a primitive function of small fx. That means when we differentiate the capital Fx, we can obtain the small fx. Furthermore, we should understand the area here refers to the signed area. That means it can be negative. We can take a look at this figure. Sometimes the area is not under the curve, but above the curve. In this region, fx is negative, and then according to this formula, when fx is negative but delta x remains positive, then we should obtain something negative. So here we can obtain a negative area, and this area is positive. In other words, when we're considering the signed area between the curve and the x-axis, when the curve is below the x-axis, the area is negative. When the curve is above the x-axis, the area is positive. Next, let's take a look at some further properties and definitions involving definite integrals. First of all, when we evaluate a definite integral, we can take out a constant, and then we can split any addition or subtraction. These two are actually the properties from the indefinite integration, and they come very naturally from the fundamental theorem of calculus. And then next, we can consider it as the definition when we swap the upper and the lower limits. If we assume that a is smaller than b, then we can actually define a definite integral in which the lower limit is greater than the upper limit. In this way, we can simply swap the two limits and then put a minus sign here. This definition also comes very naturally from the fundamental theorem of calculus. The next one is also a definition. We can define that when the lower limit is equal to the upper limit, then the definite integral is equal to 0. This makes sense because from a to a there is no area. And then when we consider the fundamental theorem of calculus, fa minus fa is equal to 0. The next one is a property of definite integrals. It says that when the upper limit of an integral is equal to the lower limit of another integral, and then when both functions are the same, then we can combine the two integrals into one, like this. This property can be illustrated graphically. From a to c, the area is here. From c to b, the area is here. When we add these two areas up, then we can obtain the area from a to b. To prove this property, we can consider the fundamental theorem of calculus. From a to c, that's capital FC minus capital FA. From c to b, that's capital FB minus capital FC. After simplification, that's capital FB minus capital FA, and that's this definite integral. And then the last property states that when we rewrite the variables into another one, it will not affect the value of the definite integral at all. The importance of this formula is to help us to realize that even though we write down x here, the result is not in terms of x. That means it seems that we have a variable x here, yet it does not appear in the final result. The final result is never in terms of x. In this way, the variable here looks like a variable, but actually it does not affect the final result. This is the concept known as dummy variables. After learning all these properties and definitions, now let's take a look at 3 examples and see how we should do definite integration. In the first example, to evaluate this definite integral, we can simply do indefinite integration first without plus c. And then we can substitute 9 into the function and then 4 into the function and then do subtraction. And that's the final result. Next, in the second example, the function is unknown and we should apply the properties that we have learned to do simplification. First of all, we should swap the 2 limits here and then make this subtraction addition. We want to do so because now we can link these 2 definite integrals into one, from 5.2 to 3.4. And then we can further link these 2 definite integrals so that now the limit is from 5.2 to 5.2. And then we have learned that it is equal to 0. Finally, let's take a look at example 3. In this example, it is possible to evaluate the definite integrals one by one and then add them up. But there is a simpler way. We have learned that this x and s are dummy variables, so I can freely rewrite all the s into x like this. Furthermore, we can see that the lower limit and the upper limit are the same for both integrals. So I can now combine the 2 definite integrals by adding the integrands. Now the integrand can be simplified as 1 over x, and now I can do indefinite integration without plus c, and then I can obtain the result is equal to log e minus log 1. That means it is equal to 1. This is how we can do definite integration. To have a quick summary, definite integrals are related to the area between the curve and the x-axis. And to find this area, we usually apply the fundamental theorem of calculus.